Dr. Please give your talk.
So thank you for the introduction. It's a pleasure to be here. It's nothing else. The weather certainly beats New Jersey at this time of year. It's very pleasant to walk around in the sun. I would like to give a talk which A, will be old-fashioned, I'm just going to write on the whiteboard. And B, it's not aimed at the experts, of whom there are several in the audience. So what I would like to do is give you some flavor of what is called Perron, sometimes called Perron-Frobenius theory. And this is just the finite dimensional version of this, which you might think of as talking about matrices with non-negative entries. Could be the subject of a whole semester course. There are books written about it on that subject alone. So let me just start with perhaps recalling, what is the basic theorem proved by Perron in, I believe, 1907. Let me give you a screen. Is this visible? No.
From the first row.
Thank you. So this is, oh.
Oh, no, it's
No, it's a question of angle. 1907. All right, so Perron is a famous German mathematician who also did work in partial differential equations, the method of sub and super solutions for solving Dirichlet's problem. But here he was interested in n by n matrices. So A is an n by n matrix. And the entries of A are real numbers. So he assumes that Aij are greater than or equal to 0. So we all know what the spectrum of A is. To give a purely algebraic definition, we say lambda is an eigenvalue of A if A times x is lambda x, where we have to be a little careful. Lambda could be a complex number in general. And x is an n by 1 vector which possibly has complex entries. So x is x1, x2, up to xn. And the xj's in general are complex numbers. And we're trying to find solutions of this. And you recall from your linear algebra course, the only assumption is x is not equal to 0. And then you write sigma of A is the set of eigenvalues. Okay. And we know there are at most n of them. So I'm recalling all these completely elementary facts because they're not going to be true when we do some generalizations. Now, at this point, let me diverge a little bit. When you take your elementary linear algebra course, they emphasize the algebra part of it. And so already you'll notice there's something a little odd here. We're not doing this over an arbitrary finite field or something like that. The entries are definitely real numbers, and that's important. Not only that, it's important if they be non-negative. Okay, so let me define R of A as the spectral radius of and R of A is by definition just the maximum of the modulus of lambda, where lambda is an eigenvalue of A. And now a tiny bit of analysis comes in. I don't want to use this formula. I mean, this is something, of course, that motivates things. But there's another way to characterize the so-called spectral radius of A. So remember, if you have any vector space, A, there's any vector space over might be infinite dimensional for that number. You can define a norm on B. So a norm on B is by definition, again, apologies to the analysts for boring everybody, but a norm on B, just so we're sure everybody's in the same boat, a norm on B is a map, usually denoted x goes to the norm of x, such that it has two properties. Norm x, or 3. Norm x equals 0 is equivalent to x equals 0. Norm, the crucial one, is the so-called triangle inequality. And finally, the norm of any scalar lambda, in this case lambda would be real, times x, is lambda absolute value times the norm of x. So if you have a vector space with a norm, it's called a normed linear space. Now in finite dimensions, this really has very little content because you prove a theorem that says any two norms on any finite dimensional vector space are equivalent. What does equivalent mean? It means that if I have a norm, let me denote it this way, and another norm denoted this way on a finite dimensional vector space, then there exist constants, positive constants, little m and capital M greater than 0, so that little m times, I'll write it this way, the norm of x less than or equal to capital, another norm of x less than or equal to capital M times the norm of x, for all x in your finite dimensional vector space. Now this is definitely false in infinite dimensions, and in finite dimensions it's true. All right, so now what does this have to do with the spectral radius? I've got a map A, which I'm thinking of as a matrix, so A, I'm in trouble. Let's move on to, A takes Rn to Rn by what? It takes, you take a column vector, an n by 1 column vector, and you just, x goes to Ax. And that defines a map of Rn to Rn, a so-called linear map. And now we define the norm of A, so I choose some norm on Rn, and then I define the norm of A to be the maximum of the norm of Ax for norm x less than or equal to 1. Okay, now that number will depend on the particular norm you choose. But the interesting fact is, if you take the limit as k goes to infinity of the norm of a to the k, this just means a multiplied by itself k times, for the 1 over k, that limit exists and it equals the spectral radius of a, and it's also just the infimum over k bigger than or equal to 1 of the norm of a to the k to the 1 over k. So now some sort of analysis is entering the picture. So now I'd like you to try to keep that in mind for future reference. And now I can tell you what one version of Perron's theorem is. So I'm not giving you the complete Perron's theorem, but let me just give you part of it. So Perron says A is an n by n non-negative matrix. Now, remember, this means in this case that Aij is greater than or equal to 0 for all I and j. Then there exists a column vector x with xj greater than or equal to 0 for 1 less than or equal to j less than or equal to n. This is x, assuming it's not identically 0, such that AX is R times X, where R is this spectral radius. So let's think about it. Step back and capture this. Let's
Maybe at the end of the marker itself.
okay, and make sure it's Ah!
First,
Maybe it really should. I didn't take the course in Rutgers. And we're still in the old system at Rutgers with actual blackboards and chalk, if you can believe that. Now, there are a couple of things to notice about this. Remember, at first blush, you might say, well, wait a minute, you aren't saying anything at all, but you are, because just because the maximum of the absolute value of the eigenvalues is R of A, doesn't mean that R of A itself is an eigenvalue. It's easy to construct examples where that might be true. Okay, so the content of this is A, that the R of A itself is an eigenvalue. Spectral radius itself is an eigenvalue. And the second piece to notice is that it has a non-negative eigenvector. Okay? Now, all right. I'd like to sketch a proof of just this fact. And the proof I'm going to sketch is going to emphasize fixed point theory, because the point of view I'm going to take in this talk is that while these seem to be, at least at the beginning, maybe even algebraic theorems, they're really best understood as a chapter in fixed point theory. That is, you reduce the whole question to a question about finding fixed points of some map of the topological space into itself. So how do you do it in this case? So this is not going to be blushing there. Okay, so proof, well, just an outline. So we first introduce the object, a natural object. We Rn plus, which I will write as K just for notational convenience, is going to be the set of column vectors x equals x1, x2, through xn, then xk greater than or equal to 0, for k between 1 and n. And if this is invisible from back there, please let me know. I'm sorry, but I'm having a little trouble. Technical difficulties, as they say. Let's define the so-called. Let's let sigma be the set of x and k, where it's the sum of the coordinates is 1. So if you were in 3 dimensions, it's easy to see what this would be. You just take the standard unit vectors, just draw the lines connecting them, and then look at the convex set spanned by those lines. It's an equilateral triangle in 3 dimensions. That would be sigma in 3 dimensions. So we define g of x. Well, this is going to be my first stab at defining g of x, and we'll see if this won't quite work. We'll define g of x to be a of x. X is this column vector, divided by the one norm of a. Where the norm of a vector y, the one norm, is the sum of the yi's in absolute value. If the yi's are all greater than or equal to 0, that would just be sum of yi's. So you'll notice that if I take any x and I look at this thing, it's going to map sigma into sigma. Of course, the trouble is it's quite possible that A times X might be 0 for some X and C. So then this won't quite work, so we do the following. We let J be the matrix with all entries 1. Instead of working with A, I work with a matrix A sub epsilon, which is A plus epsilon times J. Thank you. All right. Now, all entries of A plus epsilon J are positive, so there's no problem anymore with this definition. So we define G sub epsilon of this column vector X to be A sub epsilon times X. Epsilon is positive. Divided by this one norm of A sub epsilon. Okay. And now, somewhat, you might say, this is like pulling out a cannon to kill a mosquito. You now pull out the cannon. You say G epsilon takes sigma, which is a nice so-called compact convex set into itself. It's a continuous map. So according to the Brouwer fixed point theorem, this is the canon. Actually, the Brouwer fixed point theorem is probably misnamed, like many things in mathematics. There were much earlier results which proved it, actually. It's given his name because he did, in some sense, have the right proof from the modern viewpoint. So the Brouwer fixed point theorem says there exists an X sub epsilon, this is capital X sub epsilon, and sigma, with G sub epsilon of capital X sub epsilon equal X sub epsilon. And now if you multiply by the denominator, this tells you that A sub epsilon of X sub epsilon is some number lambda sub epsilon times X epsilon. I just multiplied by the denominator. We don't know what lambda epsilon is. It's just, this is lambda epsilon. However, you can see from the way we've done this that lambda epsilon is certainly positive. Okay? A little more thought shows you that because we added this particular matrix, every entry of A epsilon is positive. And that forces every entry of X epsilon to be positive. So X epsilon, this vector, has all positive entries. Okay? So now, it turns out that if you get one of these non-negative matrices, which has an eigenvector with all positive entries, then automatically the corresponding eigenvalue equals the spectral radius. So this is not completely obvious, and I warned you this was only a sketch of a proof. It's not a hard thing, but if I want to get anywhere, I've got to cut out some details. So lambda epsilon is R of A sub epsilon. It's the spectral radius of A sub epsilon. The rest of the proof is just a limiting argument. X epsilon lies in a compact and a bounded set. You set sigma. So let epsilon go to 0. Take a convergent subsequence for these points. So this is just the fact that a closed bounded subset of Rn is compact. So by taking a subsequence, you get sequence epsilon k going to 0 with this vector x epsilon k approaches some vector x, which has to be at sigma, and lambda epsilon k approaches lambda. And now I'll ask you to take my word for it that it is true that x is an eigenvector. That's easy to see with eigenvalue lambda. What's a little less obvious is, so what you see is that x is in sigma. A times x is lambda times x. It's a little less obvious, or again, I'm just going to wave my hands, but lambda must be equal to the spectral radius. You see, if you don't do this argument in quite this way, you might get an eigenvector, but you wouldn't necessarily know that it's the spectral radius. All right, so just trivial example. Just so you can see what, so some trivial examples are worth mentioning. You'll notice this is a matrix with non-negative entries, and you'll notice it has no eigenvector which has strictly positive entries. The spectral radius is 2, clearly. There's also another eigenvalue, 1. But in general, you will not get an eigenvector with strictly positive entries. All right, so now I want to sort of beat this particular force a little more. Suggest another proof using completely different ideas. All right, so I'm going to prove something which is less general but gives us more information and introduces ideas which actually it's sort of curious. These ideas were first published in 1957 by Garrett Birkhoff. Birkhoff gave a somewhat more general version which applied to infinite dimensional spaces, and the topologist, Samuelson. And this is an example of how things which may seem totally disconnected actually can shed a great deal of light. So the connection turns out to be something called Hilbert's projective metric. So here's the idea. Again, let me just write K, just for simplicity of notation. This is Rn plus. Please remember, these are the column vectors, all of whose entries are all non-negative. Now we look at the interior of K, and that's the set of column vectors X, all of whose entries are positive. Now, the Hilbert's projective metric I'm going to define was studied by Hilbert in 1895 in the study of non-Euclidean geometries. Okay, and it wouldn't seem on the surface to have anything whatsoever to do with this problem. The problem being eigenvectors of matrices with non-negative entries. For simplicity, I'm going to assume that A, my matrix, the n by n matrix, is such that all the entries are strictly positive. I want to define something, the Hilbert's projective metric, on the interior of this cone. Now, this is not how Hilbert did it. Okay, so the way he originally did it was he knew things about projective geometry, which used to be standard parts of the curriculum that aren't any longer. And he used that directly, and his metric originally was just defined on a convex subset, a bounded convex subset of Rn. Okay. Turns out it's actually much easier, at least if you're an analyst, to do it the way I'm going to describe. So let's define an ordering induced by K. So properly, you should write something like x less than or equal to k. The ordering is equivalent to, these are capitals, these are column vectors. Y minus x is in k. That's the definition. So I'll suppress the k. this K. So the partial ordering is defined this way. Okay? Now take two elements, X and Y, in the interior of K. It's pretty easy to see you can find numbers A, so that A times X is less than or equal to Y in this order. And Y in turn is less than or equal to B times X. The A and B are positive. Choose the largest A that makes this work and the smallest B. So there's a largest A which makes this work, smallest B. Then you define Hilbert's projective metric distance between X and Y to be the log, the natural log of B over A. I mean, you can write down a simple formula for it in terms of the coordinates of X and Y. Let me not do that. It's easy to check directly that it has the following properties. The distance of S times X to T times Y is exactly the same as the distance of X to Y for all S greater than 0, T greater than 0. So it's not exactly a metric. Because in particular, the distance of S times X to X would be 0. However, it's easy to check if you use this formulation that the distance of X to Z is less than or equal to the distance of X to Y plus the distance of Y to Z. And the third thing that's easy to check is the distance of X to Y is the same as the distance of Y. Now, what if we restrict this distance function to the interior of that same set sigma I defined before? So consider X and Y now, not on the not general things in the interior, and sigma intersected with the interior. So sigma, remember, was a set of vectors the sum of whose coordinates is 1. So fact. You'll notice that if you think of the three-dimensional case, sigma was an equilateral triangle situated like this, and this set up here, which I should probably call sigma 0, 0 sort of suggesting interior, would be the interior of that equilateral triangle. It doesn't include any of the boundary lines. The fact is that sigma 0 with the metric D is a complete metric space. As long as you just look at D on sigma 0, this problem doesn't vanish. It becomes an actual metric. Now, none of these facts is actually that hard once somebody tells you them, but somebody has to tell you them. And then here comes the real kicker. What if we look at the map G that I defined before? So what was it? I looked at A times X divided by the 1 norm of A times X. So before I had a little n and epsilon j, but A has all positive entries, so I don't need to do that. So define G of X, this is for X and this sigma 0, by G of X is A times X divided by this 1 norm. Remember, that's just the sum of the coordinates. X. Okay. G is a contraction mapping in Hilbert's projective metric. I repeat. So there exists a kappa, and we spell it out, a kappa less than 1, so the distance of g of x to g of y less than or equal to kappa times the distance of x to y for all x, y in sigma 0. Now, this is not obvious by any means. But what does it tell us? It tells us that G has a unique fixed point in sigma 0. This is the so-called contraction mapping principle. Whenever you have a complete metric space, and a map of that complete metric space into itself with this property, it has a unique fixed point. Furthermore, if you take any point x, so there exists a unique one and only one x star in sigma 0, g of x star equals x star. Okay? And furthermore, if you iterate this map for all x in sigma 0, g to the k of x, which is actually, if you just check it out, a to the kx divided by the norm of a to the k, approaches x star. And finally, if you think about it even just a little bit more, you realize this is really saying that your original A has a unique eigenvector within scalar multiples in the whole cone, because it maps everything in the cone into the interior. Every non-zero element of the cone into the interior. And this tells you how to find it. Right? This is a computationally reasonably effective way for going and finding it. Okay. So I'm not telling you any of the details about this one. And now the question is, when you have beautiful theorems like this, people try to generalize them. And I would like to have approximately half an hour. We started at 4:30. This is all meant to be by way of motivation. And, there's a whole beautiful theory of these non-negative matrices. I haven't explained where the name Frobenius came in. Remember, there was Perron-Frobenius theory in the title. What I told you is Perron didn't know about Hilbert's projective metric, but I told you basically about Perron's contribution. And Frobenius did very lovely things, which I'm not going to mention. Okay, so now the question is, if you're a mathematician and you start thinking about it, and if you're an analyst, there are many places in which positivity plays a crucial role in analysis. Okay, throw out a buzzword if you're interested in second-order elliptic equations, if you want to find positive eigenvectors to a second-order elliptic equation with, say, Dirichlet boundary conditions, well, this is going to be handled by the theory I'm describing. Okay, so things, but it wasn't at all obvious how to generalize this to infinite dimensions. So by infinite dimensions, don't panic if you haven't had your functional analysis course. I just mean I'm going to be looking at a normed vector space over the real numbers. Okay, and to make any progress in analysis, you typically need to assume things like that normed vector space is complete in the metric given by the norm. And if that's the case, for historical reasons, the normed vector space is called a Banach space. A famous Polish mathematician. So, of course, in Banach spaces, there are many kinds of cones you might look at. So the first thing we have to decide is, the cone we've been looking at, this positive ortho, the vectors, all of which whose components are greater than or equal to 0, has a number of special properties which are not true more generally. And I want to just define what I mean by a cone in general. So what is the definition of a cone? in a Banach space. So in a complete normed vector space. So the definition is, let's call it a norm vector space capital X. And for much of what I'm going to say, it's still interesting that capital X is just a finite dimensional vector space. So if you're uncomfortable with infinite dimensions, fine. But it might be infinite dimensional, by which I just mean not finite dimensional. So what do I mean by a cone C? So what are the properties? So this properly should be called a cone with vertex at 0, and it properly should be called a closed cone. So C is such a cone if whenever X and Y are elements of C, and alpha and beta are non-negative reals, alpha X plus beta Y is in C. Okay. 2, if X is in C and is not equal to 0, then we assume that minus X is not in C. And 3, just to be sure, C is closed. So this property is sort of important. And let me just write down a couple of examples of cones. So one example, so the example 1 would be the set Rn plus that I wrote before. So this is a cone in that sense. To give a somewhat more esoteric example, let's let X be the space of n by n symmetric matrices. That's a vector space. By symmetric, I just mean that you've got a matrix A transposes A. Okay. In that space, you have the so-called positive semi-definite matrices. So remember, a positive matrix is called positive semi-definite. A is positive semi-definite, or PSD, positive semi-definite. If AX inner product with X, the usual dot product in Rn, is greater than or equal to 0 for all X in Rn, column vectors. Okay, so C, the set of positive semi-definite matrices, is a cone. The set of A and X, A positive semi-definite, is a cone. Now, this doesn't really give you an idea of the enormous variety of these things when you start going into infinite dimensions. So let me just maybe mention a couple of definitions. So C, any cone, if C is a cone, it introduces a partial ordering by X less than or equal to Y and C. That's the C partial ordering, if and only if Y minus X is in C. So that's the partial ordering. Now the cone C is called normal if whenever X and Y are in C, and X is less than or equal to Y, the norm of x is less than or equal to m times the norm of y, where m is a constant, a fixed constant, independent of x and y. So this might seem really peculiar. You might say think this is always true. And in fact, it is always true in finite dimensional cones. Every finite dimensional cone is normal. But just to give you a little warning, let's look at the, so this with apologies to the non-analysts, let's look at the Banach space of one-time continuously differentiable functions from 0, 1 into R. Let C be the set of F, so the elements of F are continuously differentiable functions, and I will explain what the norm is in a second, such that F of T is greater than or equal to 0 for all T in 0, 1. Turns out that's a closed cone, but I have to tell you the norm. The norm of such an element in this Banach space X is the maximum of T in 0, 1. Well, there are many ways to do it, but let me just do it this way. Of the absolute value of f of t plus f prime of t, the derivative. Okay, so that's one of the standard norms for C1, for this Banach space. You might try to convince yourself that C is not normal. I mean, of course, this is in the old, dishonored mathematics tradition of calling something which has a property you like normal. C is not normal. Okay. Now, something which is even less intuitive if you're thinking on a finite dimensional case is it might happen that your space X can be written as C minus C, by which I mean the collection of all things of the form U minus C, U and C, and V and C. If this is the case, because of the mistranslation from the Russian, this is sometimes called a reproducing cone. I'm assured by people who actually know Russian, it should have been called a generating cone, but it's too late. So instead of that, I want to make a slight change. C is called a weaker condition. C is total if X is the closure of this collection C minus C. So C minus C is that. Now, in finite dimensions, this is meaningless. This isn't going to happen. The closure of C minus C is going to be C minus C. However, it can easily happen in infinite dimensions that a cone can be total, but not have this property. Unless you think this is really bizarre, let me give you a concrete example. Let's let X be what's sometimes called C0 of 0, 1, which is continuous maps F, which takes 0, 1 to R, and satisfy F of 0 equals 0. As usual, you take the norm of F to be the maximum for T, of absolute F of T. Now let me define a cone which is total but not reproducing. And it's a cone which comes up in practice. So C is going to be the set of F in capital X. So these are just continuous functions which vanish at the origin. F is increasing on 0, 1. And F is convex on 0, 1. Now, it's not immediately clear why this is not generating or why it's totally. But C minus C contains all C2 functions. C minus C contains all C2 functions of 0, 1, which vanish at the origin. You use that fact to prove that the closure of C minus C is all of X, but it's definitely not equal to X. So, with apologies, because I'm running out of time, I had to tell you this to explain why perhaps the most famous theorem in the subject talks about total cones instead of talking about general, let's say, cones with non-empty interior, which would be completely sufficient in finite dimension. So the most famous theorem, or one of the most famous theorems in the subject, is the crying. I have to make apologies. My original plan was to tell you also about nonlinear maps. You'll have to invite me back for that talk. It's just not going to happen. Thought I'd just polish off the linear theory. Too much of it. Okay. The history of this is, well, let me state the theorem. Work in X is a Banach space. So I'll call it a B space for Banach space, a complete norm linear space. C is a closed, so that was part of our definition, but let me just repeat it. Total cone in X. L takes X to X is the analog of a matrix. It's a so-called, is a continuous linear map. A continuous, compact, linear map. So let me, I'm allowed to do this, I guess. I had to put parentheses explaining these things. So what does linear mean? Linear just means L of alpha x plus beta y is alpha times L of x plus beta times L of y. For all x, y, and capital X, alpha and beta, this is always going to be over the reals. You know, continuous is equivalent to the sup of the norm of L of x, the norm x less than or equal to 1, is finite. So take that as the definition. And this quantity is sometimes called the norm of L. So the norm of L is by definition that quantity. Compact means that L of B closure, which is the set of things L of x, where norm x less than or equal to 1, closure is a compact set. So those are the definitions. And these conditions are satisfied from many, many examples, but by no means all examples. And now, since I gave you the definition of the spectral radius in terms of norms, I can tell you what the spectral radius of it is. R of L is by definition the limit, this limit exists, as k goes to infinity, of the norm of L to the k to the 1 over k. Right, so that would be just substitute an L to the k there, and that would give you the norm of L to the k. That's the definition. All right. Assume, now this is different from the finite dimensional case. You have to assume R of L is positive. If it's not positive, this theorem is false in general. And then there exists a B in C minus 0 with L of B equals RB and R equals R.
unfortunately, you must assume that that is positive, you didn't mention it.
Oh, thank you. Of course, I forgot, as Horace kindly pointed out to me, the most important assumption that L of K is contained in, L of C, excuse me, is contained in C. This is exactly analogous. I mean, if you think about what the Perron's theorem was in Rn, C was the positive orthant, X was Rn, L in any finite dimensional space is continuous and compact, so forget that stuff. R of L is just the way we defined it before. This condition had no analog in finite dimensions. It wasn't necessary in finite dimensions, but it is necessary in time. All right, so now I would like to spend the last 7 minutes indulging myself, and now having told you theorems which are all on the order of 60 to 70 years old at least, mention some work I'm doing now where these positive operators show up. And the question of computation of Hausdorff dimension of fractal objects. And rather than try to do this in some sort of great generality, I'm going to describe a theory which, it's a theory, it applies to many fractal objects, but I'm not going to tell you that. I'm going to just give you the example and the operator which arises. And the interesting point is, A, Ryan and Ruttman don't apply to it, generalizations do, and B, it's connected to some interesting questions about Hausdorff dimension. So here's the setup. And we now have a complete reset, move your typewriter carriage, if you know what that is anymore, whatever. So the setup is as follows. I'm going to let B be the set of things I'll call little b, which is m, things of the form m plus ni, where m is a natural number, n is an integer, I is just the square root of -1. I'll write phi sub b of z, this is when z is a complex number, to be one over z plus b. I want to look at something I'll call script I, which is all the collection of all infinite sequences of b's in there. So things of the form b1, b2, bk, and so forth. So it's conventional to write such an infinite sequence as an A. So this is where the bj's are inscribed. So we consider all such infinite sequences of things. And now you make a couple of observations that you have to sit down and work out. So one observation is that you let D be the set of points in the complex plane, with z minus a half less than or equal to a half. So it's the point 1/2, it's just a circle, the center at a half in the complex plane. We check that phi b of d is contained in D, or all D inscribed. And furthermore, that you check that they don't overlap except, they don't actually overlap. They don't overlap except in a certain trivial way. The images of phi b of D are different Ds. Now, if Z is in D, you look at phi b and omega is one of these sequences, B1, B2, BK, You look at phi b1 composed on phi b2, composed on phi bn. Okay, you check that as n goes to infinity, this converges. Converges as n goes to infinity to some numbers zeta and d. Okay, furthermore, you'll get exactly the same limit if you use a different z. The limit zeta is independent of z. So it just depends on the sequence. So you write pi of omega is zeta. Okay. These things are sometimes, the things that form pi of omega are sometimes called complex continued fractions. Complex continued fractions. So continued fractions, you'd be doing this with just the integers. Now you're doing it with all these extra things. So-called complex continued fractions. You write J to be the set of things of the form pi of omega, where omega is in this sense stripped out. So all possible sequences of that form. And you check that J is equal to phi b1 of J. J is the union of the phi b J to phi b of J's. Theta D in capital. Now, since I have 2 minutes, I can't remind you what the definition of Hausdorff dimension is, but it's a fundamental object of interest. And this set, I can't draw you a picture of it, because it's one of these fractal objects, which is highly irregular. Okay, and so one question that arises is, what is the so-called Hausdorff dimension? So there, in 1995, Molden and Urbansky, who worked extensively on sort of related questions, claim the following, that if the Hausdorff dimension, let's call it D, is D, then 1.20 is less than D is 1.9, excuse me, it was 1.20, less than 1.9. A careful proof was given of this end of it, with some allusions to computer generation. And this end, I think it's fair to say there's a certain amount of hand waving. I believe it because of subsequent work. You'll notice this is a rather large gap here. So I'm going to write down an operator which can be thought of as L sub S acting on F and Z, or Z and D. I'm purposely going to be a little vague about where F is. It might be continuously differentiable functions or twice continuously differentiable functions, or it might just be continuous. It's the sum for B. All right, go green. Sum for B, phi B. You take the derivative as a complex variable. Take its absolute value, you take it to the nth power, and you look at this. And let's suppose you look at that operator in, let's say, the space of continuous real-valued functions f defined on D. Or let's say C2 functions of D. Turns out that the spectral radius is the same whether you're in C2 of D or the continuous functions on D or whatever. For the experts, the spectrum is not the same. Definitely not. The spectral radius is the the Hausdorff dimension of J is the value of S for which the spectral radius is 1. And by doing things in this way, you have a certain amount of control. Okay? It turns out to be important to get higher order differentiability of the eigenvectors. It turns out the eigenvector, there is a strictly positive eigenvector, which is infinitely differentiable, actually. And using that, you get, in here, find the exact. So now here is the latest word. 1.854 less than 1.857 is a rigorous estimate. And this is joint work with my colleague at Rutgers, Richard Falk. But the starting point is this formula with spectral radius. So Richard Falk, so this is work in progress. And you'll notice this is considerably better than years of tape. All right, so I will stop here. Thank you for your attention.